Welcome once again in the class of the course design of steel structures. So we are learning the design of beams. So far we have learned the design of the laterally supported, laterally unsupported beams, as well as we have seen the curtailment of flange as well as the design of the built-up beams. Uh, Today we are going to solve the design procedure, see the design procedure of the built-up beam as well as the problem on the same. So I am Mr. S.S. Saugule, Assistant Professor, Civil Engineering Department. Now the design of built-up beams. Following are the design steps for laterally supported built-up beams. Ascertain the load which can be expected on the beam. Compute the maximum bending moment and maximum shear force in the beam. Compute the trial section of trial modulus of section for the compound beam by Z required equals to M divided by sigma BC or T, where this sigma BC or T is the bending stress in compression and is assumed lesser than the permissible bending stress in compression, that is for steel of FR 250 it can be assumed between 150 to 165 MPa. From the steel table choose the suitable section, furnished maximum modulus of section. The remaining modulus section will be provided by the plates as we have seen earlier by using this formula. Then calculate width and thickness of the various flange plates, curtail the flange plates. Then design the connections, calculate the bending stress in compression and tension, check the bending stress in tension, calculate the shear stress. It should be less than permissible shear stress, that is 0.4 Fy, and check the beam for the crippling if required. So this is the design procedure for the built-up beam which is laterally supported. Now design a beam with 6.5 meter effective span carrying a UDL of 40 kN per meter inclusive of self-weight. Overall depth of the beam restricted to 350 meter. See, here is the restriction of the depth is there. So that's why we are going for the built-up section. The compression flange of beam is laterally supported throughout. So the maximum bending moment, that is W into L square by 8, that is 211.25 kilonewton meter. Maximum shear force V is equals to 40 into 6.5 divided by 2, that is WL by 2, that is 130 kilonewton. Now this bending moment, that is 211.25 into 10 to 6 divided by 150. Actually the value was missing over here, that's why I've written like this. So we'll get the Z, that is 1362.9 into 10 to the mm raised to 3. So a plated will be provided. A reduced allowable bending stress at of 145 Newton per mm square is assumed to account for rivet holes in tension flange. So let us provide ISMB 225. So I will not go into deep that into steel table and all those things. So properties I have taken directly from the steel table. So area has been given, that is 3972, width, that is 110, thickness of the web has been given 11.8, thickness of the flange has been given, thickness of the flange has been given over here, that is 11.8, and web is 6.5. IXX, ZXX and H2 and G has been given over here. So we know that ZP equals to Z required minus ZXX. So we required Z is 1362 minus this what we have provided, that is this. So we are deducting this from this, so we'll get the required Z, that is Z for plates, that is 1057 into 10 raised to 3. Basically we are choosing this section because we need to keep the depth in restricted, particularly restricted, that is 350 mm. So the area of plates, that is equal to ZP divided by D. So again putting the values, 1057 into 10 raised to the 3 divided by 2 to 5. So we'll get the area, that is 4697.7. So nearly that becomes 4700 mm square. So as per IS 800 clause number 3.5.2.1, most outstand of the flange from the connection should not exceed the 16T in case of compression flange, where T1 is the aggregate thickness of the flange cover plates. So maximum outstand from the connection, that is 16T1. So 16 into 24. So we provide two plates of 12 thick. So that's why it is 24. So that becomes 384. That's 16 into 24. Here we are providing two plates of 12 So this 24 is there, and that's why it is 384. So width of the cover plate is 4700 divided by 12 into 2. So that becomes 195.83, and we are providing the 200 So outstand of the flange cover plates from the connection is 200, one half of 200 minus 60. So that is 70 which is lesser than 384. Now we are providing the plates of two plates of 200 by 12 on each flange. So IXX gross we have calculated over here. So that becomes 18,368.88 into 10 raised to 4. So this is the IXX plus 2 into AY square. That's why that's how we have calculated this one. Then this sigma BC calculated, that is this 211.25, that is the value of the bending moment, divided by this I into this Y, that is 225, that is the depth of, that is D, plus 24, that is the thickness of the 12 plates. Then that becomes 156.98. So we are checking for the bending stress in tension. Let us connect the cover plates with the flange by 20 diameter rivets. The rivets are provided in staggered pattern with two rows. The gross area of the tension flange, that is 110 into 11.8, that is this thickness B is 110. 11.8 plus 2 into 12 into 200, so that becomes 6098. That is again the area of plates. So the net area of the tension flange, that is 698 minus, we are deducting this rivet holes, so that becomes 5030 5328.3 square. So the sigma bt calculated is 156, that is this value, into this, the gross area of the tension flange or the compression flange, divided by the net area of the tension plane. So that becomes 179.65. So that is 165 Newton per square, which is unsafe. So this is unsafe. So like, let's try two 14 thick plates on each side. So again we have calculated this IXX. So that is 21,437.49 into 10 raised to 4 raised to 4. So again this sigma BC calculating, that becomes 138.45 Newton per square. Again gross area, that is 110 into 11.8 plus area of the plate. Again by deducting with the rivet holes, we will get the sigma bt calculated, that is 158.05, which is less than 165 Newton per square. So it is okay. Now we are taking check for the shear. So the shear stress, that is 130 kilonewton shear force. So this 130 into 10 raised to 3 divided by the area, that is 225 into 6.5, that is width of the web, and this is the depth. So that becomes 88.89, so which is lesser than 0.4 fy, that is 100 Newton per square. Hence it is okay. And now check for the deflection. So the deflection should be less than 20 by L by 325. So we are calculating the deflection, that is 5 by 384 into this W into L raised to 4 divided by EI. So that becomes 21.68 mm. So which is greater than this 20 mm. Since deflection is not a serious, that is only 1.68 mm is increasing. So what we are going to do, we are going to provide a camber of 5 mm may be provided. So this is the case in which the design is over. Now the design of the connection. So this is actually optional for your exam. So let's provide 20 mm diameter of rivets in two rows to connect the cover plates with flange. The rivets will be staggered. So D becomes 21.5 because we are increasing the 1.5 with the 5. So V has been given, that is 130 into 10 raised to 3. So IXX we know, we have already calculated, that is 21.37.49, and AY has been also been calculated, that is 200 into 28, that is 2 plates minus this area of this rivet, and into Y bar, that is the half the distance plus thickness of the plate. So that becomes 632.247 that is to 3. So the rivets will be in single shear as two cover plates tied together. So the strength of rivet in single shear, that is pi by 400 d square tau F. So we'll get the 36.3 kilonewton, and for bearing, that is T into B into 300, that is sigma PF. So we'll get 76.11. So the rivet value is lesser of these two, that is 36.3. So we have the formula already. So S pitch is equal to 2y divided by VAY into rivet value. So by putting all the values in the formula, we will get the pitch, that is 189.38, which is not greater than, actually which is greater than the 50 mm. So we are providing the rivets at the pitch of 160 mm. So this is for the today's lecture. We have referred the book of Design of Steel Structure as well as the IS 800 1984 and steel table as well. So this is for today's lecture. Thank you.